Good afternoon, everyone. I'm Jiyu Chen, a third-year PhD candidate from University of California, Davis. Today, I'm going to present our paper, Explore the Transformation Space for Adversarial Images. This paper is mainly about applying color and affine transformations to images to create adversarial examples without considering LP restrictions. First, let me briefly introduce some backgrounds. As we know, deep learning has been widely deployed in our daily lives in the past few years, including in entertainment and also in industry. However, we must know that these deep learning models are not robust as they appear to be. Especially in security critical tasks, those robustness failures can cause severe problems. For example, an autonomous vehicle may classify a stop sign with some stickers as a speed limit 45 sign, and that would be extremely dangerous. More generally, there exist adversarial examples, which are examples crafted from any benign examples by adding small perturbations. This is a very famous example. This panda image with a human imperceptible noise would be classified as a given by an even much higher confidence. We call the algorithm to generate such adversarial examples adversarial attacks. There are so many attacks were proposed in these years, and the most popular ones are the projected gradient descent attack and the CN doublet attack. The PGD attack tries to use the gradient descent to increase the model loss of a given example, and the CN doublet attack tries to solve an optimization problem by minimizing the perturbation added to a given image, while forcing the model to produce wrong predictions. Our proposed attacks in this paper are mainly based on these two types of attacks. Researchers also proposed many defenses to adversarial attacks. Most popular defenses can fall into two categories: adversarial training and gradient obfuscation. Unfortunately, most of the gradient obfuscation defenses are shown ineffective, while adversarial training-based defenses have the best performance so far. In our evaluations, we apply adversarial training to evaluate the strength of our attacks. One thing to mention about current popular attacks and defenses is they all consider adversarial examples that are very close to benign examples in terms of LP distances. However, there are also papers show that image classifiers are lacking robustness towards even simple transformations, such as rotations, even if these transformations keeps the image semantics. While image transformation usually cause a large LP distance, we wonder, can we automate the exploration of adversarial examples in transformation space instead of inside LP norm balls? Now, let me start to introduce our attacks. First, I will introduce what is a color transformation, considering the images in the RGB space, so that each pixel in image actually is a 3x1 RGB vector. Our transformation contains a 3x3 transformation matrix and a 3x1 bias vector. And we define the color transformation as a linear transformation applied to the pixel values, as illustrated in this figure. Note that all the pixels use the same transformation in order to keep the image semantics. The search space of a single color transformation would be too limited, so we also propose to apply image segmentation before the color transformations. Firstly, we can segment the image based on the semantics. Either use simple strategies such as looking for similar colors or more advanced image segmentation techniques. Then, we can apply a different color transformation to each of these image segments so that our search space will be much larger. Although we do not consider LP distances, we still need some metrics to measure the quality of the transformed images, because we want to keep the images still recognizable by human. We propose two metrics for transformations here. The first is we measure how large the transformation is by computing the matrix distance between our transformation matrix and the identity transformation matrix. Here we assume that larger distances are more likely to make larger transformations. The second one is the Structural Similarity Index. This is a popular metric for image quality assessment. SSIM can measure the quality of a transformed image compared with the original one by their illuminance, contrast, and structural difference. Larger SSIM means the better the quality. And we will apply these metrics in the text I'm going to introduce. The first attack we propose is the optimization attack. The goal of the optimization is to keep the transformed image semantics while making the victim classifier misclassify the transformed image into a target class. To achieve this goal, we minimize the loss function with respect to the transformation matrix. The loss consists of two terms. So the first term is transformation loss, which can either be the matrix distance or the negative of SSIM. The second term is the classification loss, which tries to maximize the model output logic of our target class. Here K is the confidence level, which controls how much larger we want the target logic to be. The optimization attack can find strong adversarial examples with the least transformation required. The second attack we propose is the PGDT, or the projected gradient descent of transformation attack. Let's see the example here. Basically, PGDT attack contains two steps. The first is to perform gradient descent with respect to the transformation matrix so that the classification error can increase. And the second step is to project the transformation matrix via one of our proposed metrics. For example, we can project the matrix to a L infinity norm ball, and which is centered at identity matrix. Here in the example, the radius is 0.25. Or we can also project the matrix so that the SSIM value is higher than some threshold. This is achieved also via iterative gradient ascent. PGDT attack may not be strong as the optimization attack, but we can use it to efficiently generate adversarial examples, especially for adversarial training. In order to make our attack space even larger, we also try to combine color transformation with affine transformation. Simple spatial transformations such as scaling, reflection, rotation, and translation, they're all affine transformations. Here we consider more general affine transformations, which are linear relocations of pixel coordinates. Since affine transformation is also controlled by transformation matrix, we can apply the optimization and PGDT attack in the same way. In addition, we propose to combine color and affine transformations to perform a combination attack. Furthermore, since our search for adversarial transformation matrices are typically start from the identity transformation matrix, our optimization still searches only the neighborhoods of the original image. To jump out of the neighborhoods, we also propose to start search from different initial points. These initial points can be obtained from simple large affine transformation, such as reflection and rotations. And that's all for our methodologies. Next, let me talk about our evaluations. We evaluated our attack on 3 datasets: SVHN, SVHN, and ImageNet. We also consider different attack settings, including the number of image segments, different initial points, and confidence levels. Let's see how different settings would affect our attack results. Here we only consider successful adversarial examples. And due to the time limit, I will only highlight our main findings. First, for color transformation, we found that if we segment the image into more pieces or segments, the quality of the adversarial examples would be higher. which means they have higher SSIM. Second, we found that combination attack has better performance than single transformation attack, either color or affine transformation. We can see that attack results of combination attack have higher SSIM and they require less transformation. Third, we found that if we start from a different initial point, for example, here we evaluated the reflection and rotation of 90 degrees, the attacks start from this different initial point would achieve better performance in terms of SSIM and the amount of transformation required. Finally, we found that larger confidence level reduces the quality of the adversarial example. This is the same as observed in LP norm-based attacks. Next, to show the strength of our attack, we will measure the success rate of our attacks on different defendant models. We will consider different retraining settings, including random data augmentation, retraining within a single attack space, and retraining within multiple attack spaces. We also compare our attack with LP norm-based optimization attacks. Similarly, we also only highlight our main observations due to a time limit. In this table, each row represents a different adversarial attack, and each column represents a different adversarial training. Each entry here is the classification accuracy of the retrained model under the adversarial attack. Our first observation is from column 1 and 2. Column 1 is a naively retrained model, and column 2 is a model retrained by randomly augmented data. We can see from these two columns that random augmentation of transformations can provide little help in robustness. For the next observation, here, row A, B, C are adversarial attacks of confidence level 0, and D, E, F are attacks of confidence level 30. Row A and D are our combined transformation attack. B, C, E, F are CN doublet attacks. We can see from these entries that when the confidence level increases, our transformation attack is more likely to transfer. Here is our observation 3. From row A, D, and G, which are all transformation attacks, we can see that our transformation attacks can reduce the model accuracy to a pretty low level, even the model is already defended, which means our transformation attacks are powerful. Our observation 4 is from the last 3 columns. They represent the models trained with multiple attack spaces. We can see their accuracies are lower than models defended in a single attack space, which indicates that training a universally robust model for all attack spaces is actually very hard. Finally, our last observation is adversarial training will reduce models' accuracy on benign examples. This is widely seen for LP norm-based adversarial training. And we also observe this phenomenon when we're training in the transformation space. Okay, that's all about evaluations. Now let's talk about limitations of our attacks. First, since we are still exploring the neighborhood of a given image, however, the transformation space actually is very large and there might be much more adversarial examples than we can find. Though we propose several methods to extend the search space, such as image segmentation, initial points, but what really can make difference here is to find a better metric. The second is compared with perturbation-based attacks, our proposed attacks require more computations for things like segmentations and transformations. So It is our future work to increase the efficiency of our attacks. Here comes the conclusions. We explored transformation space for adversarial images from the following perspectives. We considered two transformations, color and affine transformation, and their combinations. And we proposed two types of attacks, optimization and PGDT attack. And we also evaluated these attacks for undefended and defended models. As a result, we show that our proposed attacks are hard to defend. And that's all for my presentation. Thank you very much.